What's going on, everybody? Welcome back to the aromatic substitution reactions. Today I have a very quick video for you. It's going to be on the Clemmensen reduction reaction and the Gatterman-Koch reaction. First, we're going to talk about the Clemmensen reaction, which is basically taking a ketone in the aryl position, meaning directly off the aromatic ring, and reducing it, therefore dropping the oxidation number of that carbon there. So you can see here we go from C double bond O all the way to two hydrogens here. So that's reducing it. We just use a zinc amalgam. That just means zinc with mercury, and then we use hydrochloric acid. And that will facilitate that reaction. This isn't one that you'll probably be tested to know the mechanism on, because metal catalyst reactions are quite difficult for an undergrad chemistry course to understand. Our next reaction here is called the Gatterman-Koch. It's just adding an aldehyde to an aromatic compound. Quite simple, adding it to the aryl position, right? So just one directly off the benzene ring, you have a C double bond O and then a hydrogen there, giving you an aldehyde. I want to get into, before we get into the specific steps of the Gatterman-Koch reaction, I first want to give you a little puzzle. Alright, if I asked you here, what might happen with this reaction? If we take benzene and we reacted it with formal chloride here, this is what that molecule is called, this one here. Formal chloride, what do you think the product would be? Well, you might assume something like this, right? Oh my goodness, I cannot draw cyclohexane, symmetrical and well proportioned to save my life, everyone. Anyways, you might assume you'll get benzaldehyde or something through like an acylation process. Well, you'd be wrong, unfortunately, because in the lab this is not a feasible process. Now, in theory you could get this, but the species itself, formal chloride, is too reactive, right? If I were to put you in a lab and I said, I want you to make benzaldehyde for me given a bottle of formal chloride, aluminum trichloride, and liquid benzene, right? And I told you to do the reaction, I gave you a procedure, and I told you to prove it via lab report, and you go to take your NMR or IR and you see data that's not really indicative of any aldehyde groups, right? So you have no evidence of an aldehyde group being added to your benzene, and you might be a little confused as to why. That's because if I gave you a bottle of formal chloride, so let's just say I have a nice stock solution bottle of and I say it's formal chloride, and I bought it from Sigma Aldrich, let's say, you might assume that the liquid inside would be formal chloride, but that bottle has probably been at Sigma Aldrich, for example, for a couple months, right? It's been there for a while. The problem is that by the time it gets from Sigma Aldrich to me, all of it's decomposed into a bunch of side products that's not formal chloride and is not going to react with benzene most likely. So because of the very reactive nature of formal chloride, we have to do what's called make formal chloride in situ. In situ just means, okay, let's generate this reagent within the reaction mixture itself during the reaction. So what does that look like? Well, we do the Gatterman-Koch reaction, and basically the Gatterman-Koch reaction is just using carbon monoxide, hydrochloric acid, and that itself, along with aluminum trichloride and copper chloride, is going to make our formal chloride in situ in that reaction while we're doing it, and it allows it to exist and therefore react. So now, it's pretty obvious what all the first three reagents will do. Carbon monoxide, hydrochloric acid, that's going to be the building blocks of that formal chloride. Aluminum trichloride is kind of a delivery agent in a way, a good catalyst. And copper chloride, you might look at that and you're like, oh, I don't really know what that does. And to be fair, all it really does is promote the reaction to occur. It's kind of a catalyst in a way. It's a Lewis acid. That's how it reacts in this reaction. We won't really see it in the mechanism implied, but it is there helping, And if you don't have copper chloride, you have to do the reaction under very high pressures. So copper chloride is very important to this reaction. So carbon here is going to reach out to a hydrogen and dump electrons onto chlorine, giving us this molecule here. Right, so now carbon's neutral, but oxygen still has that positive charge, right? So who's happier with a positive charge? Well, if we draw the resonance structure here, we'll see that these electrons, these pi electrons, will go over to the oxygen here, giving us a carbocation, carbonyl carbon, and that invokes chlorine that we just, let me give that a fun color, which incentivizes the chlorine here to come in and snake its way in. It's like, woo, it's going to loop around and it's going to go right back and it's going to attack that carbon. All right, pretty exaggerated for no reason. So we're going to get, we'll just draw this here, and we're going to get our formal chloride. Let's draw it in orange now, because that's kind of cool for a house. Actually, I see chlorine in textbooks as green, so we'll draw the bond orange and the thing as green. And let me draw my lone pairs. So we have aluminum trichloride, and basically this chlorine will attack with one of its lone pairs to give us this. Okay, and what can be said about this molecule? Just want to point out that this chlorine is positive and this aluminum is negative. So, what do you think the next step will be? Well, if there's one thing I know in my silly little chemist brain, is that chlorine hates a positive charge. The halogens spit on that thing. I think that's what you kids say these days. So, who's happier with a positive charge, a carbon or a chlorine? Well, it ain't going to be the halogen, it's going to be the carbon. So, this sigma bond breaks, leaving us with this molecule here. And you're like, uh-oh, Cheerios, that carbon has a positive charge. And that's exactly what an electrophile is, a positively charged electron poor environment. So our aromatic finally decides it wants to join in the reaction, and we'll use a magical pink color to show that. Yoink! This will occur, and now you're going to see some similarities to Friedel-Crafts acylation here, and you're going to see, okay, we attached the benzaldehyde group, or the aryl aldehyde, but there's a positive charge. And how did we deal with that in acylation? Well, we take our catalyst here, our aluminum tetrachloride, right, with the negative charge, meaning it's quite reactive. Charges usually mean reactivity, and let's draw in a very sad hydrogen, and I'll even elaborate. If we were to zoom in on this hydrogen, we'd see a little sphere, and we'd see a little sad face, and we'd see teardrops begin to fall on this hydrogen, because you know what's going to happen to it? Well, eliminate. It's going to get freaking eliminated, and we are going to get our final amazing product of benzaldehyde, and that is the mechanism of Gatterman-Koch. Let's summarize the Gatterman-Koch reaction. Remember, Clemmensen, I'll go back real quick, is just a way to reduce aryl ketone, right? We use a zinc amalgam, which is zinc with mercury, and aqueous hydrochloric acid, and that reduces it down. So, moving on, the Gatterman-Koch. When I say Gatterman-Koch, think in your head, adding an aldehyde in the aryl position to an aromatic compound. We need to use the reagent formal chloride, but it's highly reactive, so we need to make it in situ. It's made from carbon monoxide and hydrochloric acid. I like to say it's delivered or catalyzed by aluminum trichloride, And again, we just use copper chloride or high pressures if we don't want to use copper chloride to make this reaction occur. So thank you guys for watching this video. I hope you enjoyed. I hope you learned something. This is probably one of my most favorite reactions. I suck at the mechanism and remembering it, and I had to go to a couple sources to remember just how this one worked, but it's quite a cool mechanism and how we get around some challenges in organic chemistry. There's lots of reactions like it. Same with the Clemmensens. I think that's a very cool way that we can just reduce a ketone like that very simply, right? So thank you guys so much for watching. I hope you have a wonderful day, and make sure to check out my other videos. Anyways, I'll see you in the next one. Goodbye.